Hey guys, Mr. Custis again, Penguin's math teacher, coming to you with Congruent and Similar this week. So we're only going to have a few tasks here on Khan Academy this week, but make sure, right, Thursday's into the grading period, so make sure you're getting everything turned in and completed. No blanks on Khan Academy. Let's get all those grades up here before the end of the week. So your first task this week on Khan Academy is going to be all about congruent. All right, so congruent means, let me highlight some stuff here. Congruent means two figures are the exact same shape and size. All right, this is the key here, same shape and size for congruent. All right, so with congruent, that means all the angles, all the side lengths, all the measurements, like area and perimeter, are exactly the same. All right, so if you have an angle that's 90 degrees, the new angle that corresponds to that's also going to be 90 degrees. If you had a side length that was 8, your new side length is going to be 8. Okay, whatever it is, it's exactly the same in the pre-image and the image. All right. Important to note here, congruence is a result of a rigid transformation. All right, so that's the first three that we did. That's our translations, our rotations, and our reflections, right? Those are rigid transformations, not dilations, because that changes the size. And congruent has to be the same shape and size, all right? Shape and size. So this first unit that we see, this first task for this week on congruent figures will not have dilations. All right, so we're gonna look at some of the example problems here. First question I've got here pulled up. Yuki was curious if triangle ABC was congruent to triangle FED, so she tried to map one triangle onto the other using transformations. When it says map one triangle onto the other, that just means she wants to take this one, move it over, move it up, and then get it to cover this one up exactly. All right, so if this one's the exact same shape and size, we know they're congruent, right? So I know that if I can translate this one over here and then rotate it around to make it match up perfectly, right? Notice this one wouldn't just be a reflection. Okay, if I was to just reflect it over this line, it wouldn't match up, right? Because this point here would go to there. That doesn't work, right? This angle here needs to be the same as this one. All right, hopefully you guys can kind of tell here after working with reflections and rotations that this point here is the same as this point, right? And this point here is the same as this point. Okay, so these angles, this angle is the same as this one's the same as this one. If we could rotate that around, right, this is actually a rotation here. So imagine, this being my center of rotation. If I wanted to rotate, from this point here all the way around this circle, it's looking like 180 degrees to me. If we started going around this circle, let's pick a new color. Let's say we're going counterclockwise. All right, and we went 180 degrees, right, halfway around the circle, we'd get to here, okay? So obviously then we could have also gone 180 the opposite direction right here, clockwise would get us in the same position, all right? So the movements we had to do here to get this one to match up, it had to be translated first to the right and then translated up to get this angle right here to match up to this angle right here. And then we don't reflect over this line, we actually rotate around. All right, here's our rotation point, and it rotates around. Here's the circle for this point, and all these points are moving 180 degrees. I'll show you here. If we did this point here by the F, right, that also takes what this would have been point A around the circle 180 degrees to point F. Right, and then point E here doesn't move, right? So B goes to E just with the translation. But then these other ones rotate 180 degrees around these circles, right? So Yuki concluded it's not possible to map ABC to FED. Well, we just showed that it was, right? We just showed that you could translate it right, translate it up, and then rotate 180 degrees. So she thought the triangles were not congruent, but we can tell here they are. I can tell this angle here is the same as this one. Triangle angle F here is the same as angle A, and angle B here is the same as angle E. So now we need to figure out which one of these is the reason why. All right, so says one more transformation, a rotation, would map ABC onto FED. So what they've done here is they stop at this dotted figure, right? They didn't map it all the way around. They didn't do the rotation part. So if we would have done the rotation part, then we would have seen that it matched up. The next one says one more transformation, a reflection. Well, we showed that the reflection wouldn't work, right? If we did this reflection line, I already deleted that out. We would have saw that this angle here would have gone to like here, and that wouldn't have matched up. The last choice each time says there is no error. This is a correct conclusion, and that's not correct because it says it's not congruent, but we know it is. So we were looking for the first one here because it was a rotation, like the rotation to make it match up perfectly. All right, here's another one. So again, this one says, we're mapping A, B, C, D to G, F, E, H, and they show you how we're doing it. They're showing us here, this is a translation to the left and then up, and then you can see the dotted figure here that looks just like it. This one says, let me move this over here. They're not congruent. I don't know about that. They look pretty congruent. BC here is what, 2? That would correspond to EF. That's 2. AB here is what, 1, 2, 3, 4. That'd correspond to this one, 1, 2, 3, 4. That looks pretty good too. DC is what, 1, 2, 3. HE is 1, 2, 3. Well, this last one here, A to D, from A to D, it goes what, 1 right and then 2 down. Well, this one's 1 right and 2 up. So that's the same length. Those look like they are absolutely congruent to me. But what would we have to do here to make it match up? Because they don't have it matching up yet. They're saying it's not congruent because it doesn't match up. But what would we have to do to get this one to match up? Hopefully y'all can tell at this point. This would be a reflection this time, right? Here's our reflection line if we were to flip it over. Now, this angle here matches to this one. This angle right here matches to this one. So hopefully you guys can see that. This one here would be a reflection afterwards. So this one says rotation, so that's not it. This one says it's correct, so that's not it. So here we have the correct answer. All right, here's our reflection. That's the one that we're looking for. All right, I'm not going to do all of these, but I'll definitely do a few more here to kind of demonstrate, and hopefully you guys will pick this up and it won't be too bad this week. Again, this one says not congruent. We're talking about line segments this time. So we have JK, that's this one. And we have NM, so here's N to M, that's this one. All right, and it says not congruent. So for line segments, there's really not a shape. It's just, part of a line with endpoints here and here, here and here. So we just need to see are they the same length, right? If they're the same length, then I know these two are congruent. So what I'm going to do here is I'm going to count. And I'm just going to say, okay, well, this one goes 1, 2, 3, 4, 5 to the right, and then 1, 2, 3, 4, 5 up. All right, so this one's also 5 and 5 to get from the bottom to the top. Then yeah, I think they're the same length, and they're congruent. So this is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So yeah, these are congruent. Again, we're seeing that they're saying they're not, but they actually are. So we can't say there's no error. There is definitely an error there. What would we need to do here? What they've done here is they've translated up this line to get point J here onto point N. And how could we get that one to come over here? I think the easiest way here would probably be a rotation. All right, so if N here is at my middle, let's see what that rotation would be. If I go around the circle counterclockwise, that looks to me like we are creating a 90-degree angle right here. So I'm going to say that's 90 degrees counterclockwise rotation. So let's highlight that one. That's our rotation. Here's our rotation. So I'd say this one, right? So it's not going to be a translation here. This time they didn't say rotation or reflection because there probably is a line there that we could have reflected it over that would have made it match up. Let's maybe extra credit here, but I think, you know, maybe if we had a line right here in the middle, we could have also reflected that over to make it match up too. All right, let's maybe do one more here. This one might look a little bit trickier. So let's do one more here on congruent, and then we'll look at some similar figures too. So here we've got a triangle ABC going to triangle FED, and again saying not congruent. All right, not congruent. But I think we might find differently here. All right. So what they've done is they've translated, but they didn't try to reflect it here or try to rotate it to make it match up perfectly. It looks like they're about the same size though, right? So let's see what happens here if we try a rotation here around the middle of this. And let's go here through the middle. It's a little bit off there, isn't it? If we go right through the middle of that circle, it's slightly off. It's not quite 180 degrees around. All right, we'd want to go 180 to get to D there. And that could just be here because of this this program I'm using doesn't make it look just perfect. But our other option here would be to do a reflection, and a reflection is definitely not going to make it match up. If we reflect, right? Let's see. Let me get it better. This point here was what, 1, 2, 3, 4, 5 to the right, so it would be 1, 2, 3, 4, 5 to the left. If we were to, my crayon's not the best here. If we were to reflect that point, then point C here, right? Point C doesn't end up exactly where we need it. So yeah, it's definitely not a reflection. It looks to me like it's got to be a rotation. So that definitely doesn't work. But it does look to me like it probably is. Let me get rid of some of this stuff so we can see. It definitely does look like it's going to be congruent, the same exact shape and size. If we want to count these links, let me get a highlighter here. This is what 1, 2, 3, 4. Obviously, it's the same. It's sharing that side length here from E or B to C, or right here. This is what, up 1, 2, 3, and right 1, 2, 3, 4, 5. So here, right, this is 1, 2, 3, 4, 5 to the line, and down up 1, 2. And this one's down 1, 2, and right 1, 2, 3, 4, 5. So that's looking like it's not congruent. So I'd have to agree here. I thought maybe we could reflect or rotate that one around, but I don't think we can. I think that's going to be correct as is. I don't think those are congruent. I would go with not congruent for that one. All right. Let's see if there's any other variations here. We got more line segments. We've looked at those. This one here could be a little tricky. Make sure you're checking this one out. This bottom here is 1, 2, 3. This one's 1, 2, 3. But now they've changed this one here. It's 1, 2, 3, 4, 5 tall. But this one here was only 1, 2, 3, 4 tall. All right, so this got taller. Right, we can see that it's taller over here than it was here. So hopefully you realize what that means for the congruent or not congruent there. All right. Yeah, so definitely just check the size, check the shape. Make sure that if you're going to say they're congruent, that you're saying they're the exact same shape and size. All right, all the angles have to be the same, and all the side lengths have to be the same. Something special here, they use the word coincide. So if it says circles A and B coincide, that means there's actually two circles here. We can only see one, but this is actually circle A and B. All right, so B is right here on top of A. You just can't really see them both. All right, so hopefully that lets you know, right? Those are the exact same shape and size if they coincide they're on top of each other. That's why you can't tell there's more than one. So again, here we see that word coincide again. All right, so coincide means you can't see that there's two line segments here. You see the points, they've got the points labeled as A and C and B and D. And you just can't tell because they're right on top of each other, right? So the other line segment here is literally right on top of the one you can see there. All right, so hopefully that tells you whether they're congruent or not. Pretty straightforward there with some triangles. Whoops, why is that one getting bigger? What's that tell us? Let's see, are congruent. I don't know. I don't think circle M and circle N. Yeah, maybe we translate over here from circle M to N. Translation and dilation. So that's something we talked about at the very beginning, right? Whenever you see a dilation, we know that they are not congruent, okay? So that's not going to work. Right, dilations change the size, so we cannot say they're congruent. Right, so she didn't use only rigid transformations. She used only transformations, but not rigid transformations, right? Because the dilation is not a type of a rigid transformation. Special care on this one here. This one might initially look like the angles are all the same. Check this one out though. What's that tell us? Right, that little box. And we don't have one over here. All right. This angle here is obtuse. This one here must be 90 degrees. So what's that tell us? Does that tell us they are congruent or not? All right, remember, if the angles change, they are not congruent. The angles have to be the exact same for congruency. This is a fairly easy one. If you count here and then count here, you should see, about those side lengths. All right, and the size changes, we know it's a dilation, not a rigid transformation. So that's the first task. That's all the congruent problems. Now, similar is next. So similar is very, very similar to congruent, but it's slightly different. All right, similar is the same shape still, all right? The same shape, but different size. So if we do a dilation, right, and the size changes, that's when we can use the word similar, but we can't use congruent anymore. All right, so similar occurs whenever we have a dilation. All right, so what that tells us then is the angles are going to stay the exact same. Angles stay the same, but side lengths, perimeter area, those things are all going to change. All right, whenever the size changes, all right, then the side lengths get different, the perimeter gets different, the area gets different, but the angles stay the same. All right, the angles stay the same. So if it's a 90-degree angle, it's still a 90-degree angle. All right, if it's 180-degree angle, if it was a straight line, it's still going to be a straight line. Okay, if it was a circle, it's still going to be a circle. And it's just going to be bigger, right? So shape stay the same, but the size changes, right? So here we see a couple of strange quadrilaterals. We have OPQR, OPQR, and ONML. ONML. It says using a reflection and a dilation. So it looks to me like first they reflected this one. Here's the reflection line, right? They took it and they flipped it over that way, and then they dilated it. So after that initial reflection, right, we see here's the new dotted lines here, and then it was dilated. So all these points are getting further away, right? So this one right here was what, 1 to the left and 2 up. So now it looks like it's double that far. It's 2 to the left and 4 up. All right. M was what, 1, 2, 3 left and 1 down. So now it needs to be double as well if it's a correct dilation, right? 1, 2, 3, 4, 5, 6 left and 2 down. So those are both doubled. Point was that R was here, 1, 2, and 1, 2. So now it's going to be 4 and 4. 1, 2, 3, 4, and 1, 2, 3, 4. All right, so they did the dilation right. That's going to make it similar. That's going to make it match up. So let's look at our options here. Bastian used a reflection, so the quadrilaterals aren't similar. Not true. All right, the reflection, if it was just a reflection, then we would say they're congruent. But since a reflection and a dilation, then we'd say they're similar. Bastian used a dilation, so the quadrilaterals aren't similar. Anytime we use a dilation, they're still going to be similar. So there's no error. This is the correct conclusion. All right, this one's going to be pretty straightforward. Anytime you have line segments are always going to be the same shape, right? There's different lengths. So there's definitely a number here that I could multiply AB by. I don't know that exact length. Later in the year, we'll use Pythagorean theorem and we'll be able to find that. We do 1 squared plus 2 squared. So square root of 5 would technically be the length here. That's something we'll do later this year. And then we'd find this length and we could find the actual scale factor. That's not important for now. But you know, that's something that we're going to get to. But for now, let's just see that we can rotate this over and then we could dilate it to make it larger and make it match. It looks like it's about 2 times as big. So maybe this one's a square root of 10. I'm not going to calculate it here. But this says that they are similar. So that's definitely true. These are similar. Let's read through here. Aaron used a dilation, so the segments aren't similar. No, we know, right? Dilations keep them similar, right? The segments are congruent. No, they're not congruent. Those aren't the same size, so they can't be congruent. All right, so we know that part's not true. There is no error. Yep. So this one's correct. All right. Maybe look at 1 or 2 more here. Eleanor is curious of triangles DEF. So here is DEF and GHI. Were similar. So she tried to map one figure onto the other using rigid transformations. So the first thing I see here is a translation, taking point D to G, point E up to here, and point F to here. All right, so all those points were translated the same distance and direction, so that part's correct. And then it looks like they had to dilate it to make it smaller next. Right, that one's too big. She's saying they're not similar. Let's see why. Let's see why she thinks we can't map them up. So it says one more transformation, a rotation would map DEF onto GHI. Well, that's not true, right? This dotted line one here isn't going to get matched up by a rotation. It's got to get smaller. So this says one more transformation. A dilation would map triangle DEF onto triangle GHI. So the triangles are similar. Well, that's true, right? We got to make this smaller. We got to shrink it down to match up, and be this smaller triangle right here. So if we did this dilation, that's how we would make it match up perfectly. All right, so we're looking for B there. All right, we've got some more examples here. Again, we got some line segments. So hopefully, right, line segments are going to be similar, just not congruent. This one here perhaps could be tricky. We see, here's this quadrilateral EJGK, and then I'll use a different color here for EFGH. All right, hopefully you can tell these are not the same shape. All right, we cannot stretch / move 2 of the points and not the other 2. Okay, this one's only being stretched vertically. It's not being stretched horizontally as well. All right, if we dilate it, all the points except for potentially the center of dilation point being on the shape all have to move. Okay, we cannot move 2 and not the other 2. We could move 3 and not the last one if the last one was the center of dilation, but we can't move 2 and then leave 2 the same. All right, so we cannot just stretch it vertically here. We can't just move J to F and K to H and say that they're similar. That's not going to work. All right, here, check this one out. Links. All right, when some change and some don't, that's not a correct dilation. Okay, so be careful with those. We can't say they're similar if we don't dilate it correctly. All right, got some triangles, some more quadrilaterals. And then we have some questions like these. I did want to go over this rectangle question. So it says a rectangle is either sometimes, always, or never similar to another rectangle because we can map one onto the other using only dilations and rigid transformations. So if I had this one and let's say this one, right? I can't map this one onto this one, right? Because they're different. They're different shapes. They're both rectangles, but I'm not, because this one's so much skinnier. That's why it's not gonna be able to be dilated, right? Because I'm gonna dilate, I've got to change this distance and this distance by the same amount. I gotta cut them both in half, or double both of them, and that's not gonna work for this triangle, right? But it could possibly work, right? If I had this triangle here, I could make it match up perfectly to another one. I could bring it down here and then shrink it the same amount vertically and horizontally. So sometimes I can make rectangles match up, but not always. All right, so sometimes, definitely not always, definitely not never either. All right, so this is the sometimes one here. All right, we've got a few of these. Again, circles are always the same shape. So we should always be able to do a correct dilation and get those to match up. We got another one here, equilateral triangles. So let's talk about what an equilateral triangle is for a second. Here's an equilateral triangle. That means all of these angles are 60 degrees. And then a scalene, scalene means that all of the angles are different. I'm not sure. Yeah, I think I can draw a scalene on here. Yeah, so here's a scalene, right? So an equilateral triangle here is sometimes, always, or never similar to a scalene triangle. So would we say that these angles here are the same as these angles here sometimes, always, or never? All right, so think about, this angle measure here, this angle here. These are all 60. Are these all going to be 60? All right, so sometimes, always, or never on that one there. And then line segments, we did a few of those, and we talked about a few of those line segments, as well as the circles. All right, and we see another circles problem here to end things out. All right, so hopefully this helps. Remember, guys, three assignments for this week. You've got your congruent assignment in Khan Academy. You have your similar assignment in Khan Academy, and then you have the quiz. All right, so please try those as many times as you'd like. Keep trying them. Come to our office hours and get help. But please get 4 out of 4 on congruent. Get 4 out of 4 on similar. Get 5 out of 5 on that quiz. Right? Remember, those quizzes are worth half of your grade. Those are worth 50% of your grade. So that's the biggest part. So make sure that you're doing your best on those quizzes. That's the easiest way to bring your grade up. All right, and remember, grading periods ends on Thursday. So you got to get everything that we've been working on finished up by Thursday, right? All these past ones, all the transformations, translations, rotations, reflections, dilations, right? Make sure you have all those attempted by Thursday. If you'd like an A, make sure you get 4 out of 4s and 5 out of 5s and all that, right? Thanks, guys. Hope this helps. But again, check in with your teacher if you're struggling. If you need more help, we'll be happy to help you during your office hours. Thanks, guys. Have a great week.